All right, guys. So here's the homework that you can pick up for the previous one. And also the new homework is due this Thursday, right? And then next Tuesday we will have a midterm exam. Okay. So we are discussing about this orthogonal set, which is a more strict version of the linearly independent set. And then we learned about how to compute this linear combination coefficient when given a basis, orthogonal basis that spans our subspace W, right? And then that coefficient is represented in this form. Okay. And then we learned about this orthogonal projection when given a single vector. So basically we can decompose any given vector y in Rn into two parts, which is inside of W, and then which is included in W perpendicular. And so this y hat is called orthogonal projection, and intuitive meaning of it is basically the perpendicular projection from any vector y onto our subspace W. But in this particular case, our subspace W is spanned by single vector u. Okay, and so this orthogonal projection y hat can be represented as a linear combination, or basically scalar multiple of the single basis vector u. So here, our problem is to obtain this alpha, which is a scalar multiple for given a basis vector. And here in this y hat, our requirement is that this angle here to be 90 degree. Okay, so that way we obtained the alpha hat, and in that case this y hat, and the corresponding linear combination coefficient alpha is represented in this form. Okay, and then y hat is a scalar multiple of u. Okay, so that is formally called this orthogonal projection of y, which is any vector in our space, onto our subspace W. But in this particular case, since our subspace W is just a single line, L, so that's why we call that as just L in this particular case, because it's spanned by only one vector. And some example that you can easily study. Okay, so in this case, we are given u here, and then any vector y, and then we can think of orthogonal projection y hat, which is a 90 degree here, and then this vector y is decomposed as this guy, which is y hat, and then this guy, which is z, and then z is just a difference from y and y hat. Okay, and so here the two vector, this guy and this guy, should be perpendicular. Okay. Okay, now here's the new concept or new notion that we will learn today, which is instead of orthogonal, we will learn about this orthonormal. Okay, this orthonormal is more strict version of orthogonal vector or orthonormal set. So we have orthogonal relationship, which is just a perpendicular from each other. And then when given this set of vectors, each of the vectors should have the length of 1. Okay, so that not only having the angle of 90 degrees, but also each vector should have the length of 1. Okay, so yeah, while maintaining or while keeping the angle as the same as this 90 degree, but also we can freely scale up or down or change basically the length of the vector that we have into just a unit length or the length of 1. Okay, so yeah, let's think about this simple case of. So in this case, suppose this orthogonal set where we have these two vectors, but what should we have in this value so that they are orthogonal? What is this value? Just 1, right? So it should be 1 because suppose this guy is V1 and V2. We want V1 dot V2, which is the inner product between them. Should be 0, right? So this guy should be 1, so that the inner product can be 0. But in this case, they are orthogonal set, but they are not orthonormal set because they are not normalized. In other words, their length is not yet 1, right? So in this case, we have a so we have a vector of 1 comma minus 1. So we have a vector here, and the length of this vector is certainly not 1, right? So in order to normalize this vector, or in order to make the length of this vector as 1, we can simply just compute their length, which is this guy. 1 squared and minus 1 squared, which is 2. And so this is the squared length, right? So the squared length of this vector, and then square 2 is the length of this vector, right? And so we basically divide each component by this length of the vector. Okay, so in this case, the orthonormal basis or orthonormal set is square root 2, 1 over square root 2 and minus 1 over square root 2. Okay, and then also we can normalize this vector in the same way so that their length is 1. Okay, so that's quite simple. So again, this orthonormal set has two conditions of orthogonality and also having the length of 1. And also, we know that this orthogonality is more strict condition than a linearly independent condition. So if they are orthogonal, and then they are automatically linearly independent, right? So if we think about the span formed by this orthonormal set, okay, and then they are automatically becomes the basis for that subspace because they are already linearly independent, and then we think about the span of these vectors, right? So these vectors again are spanning the space, and also they are linearly independent. So they are automatically becoming the basis for that subspace, and especially this basis can be called this orthonormal basis, okay? Because the vectors in our basis set are all orthonormal. Okay. And in this case, the simplest example is shown as this guy, which is called this standard basis. I guess we haven't had a chance to discuss much about this standard basis, but this standard basis is really simple set of bases. So if Rn is like R4, then we have 4 standard basis vectors where only one entry is 1 and all the other are 0. So 1, 0, 0, 0, and 0, 1, 0, 0, and so on, right? So we have 2 more vectors to form or span the entire space of R4. Okay, and then let's think about the following question. So particularly in R4. So when thinking about R4, how many linearly independent vectors can we form? So again, the question is, what is the number or the maximum number of vectors that are linearly independent in R4? 4, right? And then let me change this question in the following way. So how many? What is the maximum number of vectors that are orthogonal in R4? And it's also 4, right? So in R4, we can only find 4 different orthogonal vectors, right? We have to draw this 4-dimensional space, which is not possible. But anyways, so you guys already know about this linear independence, the notion of a linear independence, and also more strict version of this orthogonal and also orthonormal basis. Okay. There's another simple example where we have these 3 vectors that are all orthonormal. So if we compute the inner product between any pair of these 3 vectors, and then their inner product should be 0, and then also if we compute the length of the vectors, which is the inner product between the same vectors, right? This is typo, okay? So this should be the length of 1. So the length of each vector should be 1. Okay, so that is the additional condition that we have in the case of this orthonormal set. Okay, and then a few theorems that we can learn at the end of this this chapter. So theorem 6 says, when given this m by n matrix U, and U has orthonormal columns. Okay, so suppose m is 4 and n is 3. So we have 3 vectors in 4-dimensional space. Okay, so this is our U. Okay, so this, and then let's call each of these column vectors as U1. So this is a large U, which represents a matrix, and each column vector in this matrix as U1 and U2 and U3 in lowercase. Okay, and then the condition here, or the assumption, is that these vectors U1, U2, U3 are orthonormal, which means their length is 1, and then each pair among these 3 vectors are all perpendicular to each other, or their inner product should be 0. Okay. So when our matrix has these orthonormal columns, and then this theorem says U transpose U is identity. Okay. Then let's think about this. First of all, let's think about the size of this identity matrix. What should be the size of identity matrix? Should it be 4 by 4 or 3 by 3? It should be 3 by 3, right? So in the case of U transpose, if we transpose this matrix, then we have 3 rows, so it's 3 by 4, right? And also we can call that as U1 transpose, because this guy is transposed into a row vector, right? U1 transpose, U2 transpose, U3 transpose, and then we multiply it with U1 and U2 and U3. Okay, and then we can rewrite this guy into this form. Okay, so it's the same representation as this shape. So here we have this row vector, and then we have a column vector in here. Okay, and then it's again it's a 3 by 3. The size is 3 by 3, and then let's consider how we compute this 1 comma 1 component. In this case, it's gonna be the inner product with this row and this column, right? And so it's a U1 transpose, which is this guy, row vector, and U1, which is a column vector. And then since we know the inner product between the U1 and U1, which is between its U1 itself, should be 1 because their length is 1. So it should be 1, and in the same way, this should be also 1. Okay, and what about the off-diagonal parts? In this case, it's going to be corresponding to the multiplication of this guy and also this guy, U1 transpose and U2, which is 0 because they are orthogonal to each other, right? Okay, so that way, U transpose U is always identity matrix. Okay, so this orthonormal, the matrix that has orthonormal columns has this interesting properties, and also, as we will learn in the next chapter, we will also learn about this form, U and U transpose. Okay, so in this case, instead of multiplying U transpose and U, so we just switch the order between U and U transpose. So in this case, the matrix will have the size of 4 by 4, and this is called projection matrix. Okay, but we will learn about it later today, I guess, in the next chapter. Okay. I actually rehearsed today's lecture using the new device. But anyways, okay, so this is the last theorem that we will learn in this chapter. So we learned about this U, where the columns of U are orthonormal columns. Okay, so you can think about it as this guy, where we have 3 columns in 4 by 3 dimensions. Okay, and then basically they have these 3 different properties, and then the first property is about the length. When transforming a vector x using this U, okay, so in the case of an x, what should be the size of an x when multiplied on the right side of U? So what should be the size when multiplying x on this side? So this is an x. How many elements should we have? 3 or 4? 3 or 4? 3 or 4? Okay, let's take a poll. 3 or 4? So it should be 3, right? Because it has 3 columns, right? And then, so we learned about this form, A times X. And in this case, we can view or think of this multiplication as the linear combination of the columns of an A, right? And then this column vector X should have the same same number of elements as the number of columns, right? So if it is 1, 2, 3 for our vector X, and then it means, so in this case, this UX means the linear combination of these 3 columns with the scalar multiple of 3 times 2 and times 1, right? And then we add them together to form a single vector. Okay, so that's what we learned a lot previously. Okay, so in this case, the length of this vector, which is represented as this form, is the same as the length of the original vector x. Okay, so we don't know what this u1 and u2 and u3, and then the dimension of this, the length of the vector of u1 and u2 and u3 can be really large. So yeah, let's keep the number of column vectors as 3, but it can be like 100-dimensional space. So each column can be really long and thin column vectors. Okay, but in this case, if we consider their linear combination with the linear combination coefficient of 3, 2, 1, and then the resulting vector will be also 100-dimensional vector. And then we compute their length. How? We just take the square of each element of each of these 100-dimensional elements, and then take the square root of it. And that's the meaning of this guy, which is the length of that vector. Okay? And then the length of that vector is just simply the same as 1 squared, 2 squared, and 3 squared. And then take the square root of it. Okay? Okay, so the proof is really simple. So the trick is, in the case of this, yeah, we can first think of it as a squared version of the length. Okay, and then it's going to be the same as this. The squared length of the vector is the inner product of the same vectors, right? So still, this is an inner product. Okay, and also this case we can represent it as this guy. It's the transpose and ux. So here this is a bigger dot and this is a smaller dot. So this has a special operator that performs the inner product, right? So yeah. So is it a valid representation or not? So it is valid representation because this represents the inner product operator. Okay, and then when computing it, we perform or we take the transpose of it and then multiply this vector, and basically this is a matrix multiplication. It's the same as this inner product operator. So it's if we consider the size, it's a 1 by 3 because it has 1 row and 3 columns, and in this case 3 by 1. Okay, and so resulting matrix is basically 1 by 1, which is a scalar, right? So that's how we perform this inner product. Okay, and so up to this point it's still a column vector here, but in this case now it's a row vector. And then in this case, this guy is this guy, right? So yeah, by applying the distributive law of this transpose operator, and then their order is changing. Okay. So in this case, the U transpose U becomes just identity, right? Because of this theorem 6, right? So it becomes the same as U transpose X transpose X, and thus it can also be changed into this form. Okay, so we started from here, and this guy is the same as this guy. Okay. Okay, and then similarly we can also prove this guy and also this guy. So not only just the length of a single vector, if we consider two vector x and y, and then we can consider the transformation of each vector through this matrix U, and then their inner product will become the same as this guy. Okay, and then if these two vectors are having a 90 degrees or perpendicular to each other, and then the original vector x and y is also perpendicular to each other. So again, this guy is living in, for example, our 100 space. And then this guy is living in R3, for example, in this case. Okay. So from these three properties, we can see this matrix U that have this orthonormal columns will preserve the length and this orthogonality. Okay. B랑 C요? B랑 C도 증명 똑같이 되는데. Okay, so yeah, the proof is also in the same way as this guy. So let's simply prove this B. So in this case, it's gonna be X transpose U transpose, and then U and Y, right? So this inner product operator, okay, will be changed into transpose, and then this guy, right? So we always see this U transpose U, which is an identity, and thus it's gonna be X transpose Y, and thus by using the inner product operator, we can write it in this form. Okay. So in this specific example, does anyone recall anything related to this that among what we learned previously? So so we basically change this a vector in R100 into R3. Okay, so this is really long and thin vector where we have 100 dimensions, and then this vector is changed into this 3-dimensional vector, or it can be changed into this 100-dimensional vector. Anything ringing up? Yeah, anything related to this? So yeah, we learned about this something called some coordinates, right? So suppose we have V1 and V2 and V3, and then we consider the span of these three vectors, and then let's think about some vector B which is living in this span. So let's call this guy as subspace W, and then let's consider a vector B which is inside of this subspace W. Okay, and then this is a very long and thin vector, like a 100-dimensional vector. And also this B is also R100. Okay, and then what is the coordinates of this guy? Okay, let's call that as Y. So the vector Y, and then we learned about this new coordinate of this 100-dimensional vector Y. So this is again 100-dimensional vector, but this is inside of this subspace W, which means this guy is represented as linear combination of V1, V2, and V3. Okay, and then what was this B coordinates, where the basis B is this three vectors, V1, V2, and V3. So it was called coordinates with respect to this basis B, and also it is now living in this three-dimensional space where we have three different numbers, and each number is just nothing but the linear combination of this linear combination coefficient when representing this vector y into this guy. Okay, so this C1 and C2, C3 will be our new coordinate in three-dimensional vector. Okay, so here, when thinking about this theorem that we saw in this case, so we think of this so two vectors, y1 and y2, which is living in 100-dimensional vectors, 100-dimensional space, but they are inside of our subspace W. But here we have one additional condition where v1, v2, v3 are not only linearly independent, but they are also orthogonal to each other. They are perpendicular to each other, and also their length is 1. Okay, so that is what we call this orthonormal vectors. So when our basis vectors are orthonormal set, in that case, when picking up these two vectors, which is inside of our subspace W, and then their lengths will be preserved after we think about this, after we obtain their, suppose this one was y1, and this three-dimensional vector is called x1, for example. Okay, so this 100-dimensional vector is now represented as vector x1, which has these three-dimensional vectors. So this x2. Okay, and so the length of this 100-dimensional vector will be preserved after we obtain this b coordinates by using orthonormal basis. And also, if two vectors were perpendicular to each other, okay, and then also x1 will be perpendicular to x2. Okay, and also basically all the angles will be preserved. Okay, so in this case, so what is the meaning of this guy in the case of second one? It's the inner product between this vector and this vector, right? And the inner product of these two vectors, so you guys know this formula. So we have a vector x. So let's consider the vector a1, a and b, and so this is like maybe four-dimensional vectors, two four-dimensional vectors. Okay, so this is a completely different case. I'm just talking about the properties or characteristics of this inner product. So in the case of a dot b, or the inner product between a and b, can be represented as this guy. Cosine theta, right? So this one was ux and uy, okay, and then the theorem says this guy is the inner product between the x and y, which is a b coordinate of this ux and uy. Okay, so in this case, we know the length of each vector is preserved. So when thinking about the inner product between these two, and then they will be composed of this length of each vector times cosine theta, which is the angle between these two. Okay, and then also in the case of an inner product of this three-dimensional vector, they will be also considered as this guy, right? So this is of course theta 1 and theta 2. So the lengths of each vectors are preserved. The length of this guy and length of this guy will be the same, and the length of this guy and the length of this guy will also be the same, and thus based on the fact that their inner product are the same, their cosine theta value, or the angle between these two, should be the same. But again, the angle between, so angle here is formed by these two vectors, which are 100-dimensional vectors. So we have two vectors that are in 100-dimensional space, and their angle is actually the same after we change them into b coordinate of each vector, and then considering their angle, and then the angle is preserved as the same. Okay. Okay, so this orthogonality is simply saying that this transformation preserves the angle of 90 degrees, right? So it's a little one particular example when the angle is particularly 90 degrees, but actually all the angles are preserved, even they are not even if they are not even if they are not 90 degrees, if they are like 30 degrees, and then this 30 degrees will be exactly preserved as well. 네.
x를 그럼 코디네이트라고 생각하면
그렇죠. 맞아요.
그럼 이렇게 반대로 돼야 되나?
네, 그러니까 여기서는 이제 식을 이 왼쪽 거부터 먼저 따지면, 왼쪽 거부터 먼저 따지면, 네, 이 왼쪽 거가 어떻게 보면 코디네이션이 먼저 주어진 거예요. 그러니까 그 전에는 100-dimensional 벡터가 있었고, 그 다음엔 베이시스 벡터가 있어요. 그 다음엔 그거를 이제 그 100-dimensional 벡터를 뭐 예를 들면 그 100-dimensional 벡터를 예를 들면 b라고 했을 때 그 b equal ax를 풀어서 이제 그 리니어 시스템을 구했을 때 이 100-dimensional 벡터가 있고 이게 베이시스 벡터다. 그럼 이게 b고 이렇게 했을 때 여기에 x1, x2, x3 요 값을 구하는 게 우리가 b 코디네이트 그걸 구하는 거였죠. 그죠? 근데 여기서는 조금 반대죠. 그러니까 이게 지금 주어져 있는 거예요. 이게 주어져 있고 우리가 이거를 지금 상상하는 거예요. 이 100-dimensional 벡터를. 그러니까 여기서는 뭔가 여러분들이 코디네이트를 리니어 시스템을 풀어서 구해야 될 필요는 없는 거고, 요게 이미 주어져 있고, 그 다음에 이 리니어 컨비네이션을 생각을 했을 때, 혹은 이 u랑 이제 x, u를 통해서 이 x 벡터를 트랜스폼을 했을 때, 근데 이 트랜스포메이션은 어떤 거냐? 이게 훨씬 더 작은 애고, 이게 R3고, 이 ux or y belongs to, for example, R100. 이런 관계를 지금 생각하고 있는 거고요. 그래서 여기서 지금 이야기한 것처럼 여기서 x가 우리가 이야기하는 b 코디네이트이 되는 거고요. 그 다음에 ux는 이 굉장히 긴 벡터가 되는 거죠. Any other questions? 네. 네. 자, 이게 뭐냐 하면 우리가 3차원에 있어요. 그리고 3차원에서 서브스페이스를 2차원 두 개의 역시 직교하는 어떤 베이시스에서 스팬되는 스페이스를 생각을 하면, 근데 일단은 이게 손가락이 방향만 중요한 게 아니라 길이도 1이어야 돼요. 손가락 길이를 1이라고 생각하자고요. 쫙 있고 그랬을 때 어떤 이 스페이스 내에 벡터 하나를 잡아요. 이거는 지금 3차원에 있는 벡터예요. 다만 우리의 서브스페이스 내에 포함이 쏙 되어져 있는 벡터죠. 그죠? 이 벡터에 대한 좌표값이 있겠죠. 3차원 좌표값. 그러니까 예를 들어서 여기가 x, 이거는 우리의 also normal basis 벡터고, x축, y축, z축 있잖아요. 그걸 x축, y축, z축 이렇게 있다고 해봐요. 우리가 일반적으로 생각하는. 그럼 요 좌표가 x축으로는 좌표값, y축으로 좌표값, z축으로 좌표값이 있을 거예요. 그죠? 다만 얘는 얘 스페이스 내에 있기 때문에 이 좌표값이 뭐 1, 2, 3이다. 그러면 얘는 요 두 개로 리니어 컨비네이션으로 표현이 되겠죠. 그죠? 그럼 요 1, 2, 3의 길이는 그러면은 1제곱, 2제곱, 3제곱 다 더한 다음에 스퀘어 루트. 그게 이 벡터의 길이가 돼요. 이거 생각 안 하고 이 3차원 스페이스에서 그냥 얘 1, 2, 3 좌표값의 길이. 이 길이는 이 올소노멀 베이시스로 얘를 나타내요. 그랬을 때 그 좌표값이 뭐 그 좌표값은 구할 수 있죠. 이게 이 리니어 컨비네이션 코에피션트, 즉 요 벡터 길이의 몇 배를 가야, 그리고 요 벡터로도 몇 배를 가야, 그 배수가 그 리니어 컨비네이션 코에피션트였죠. 그 배수가 우리한테는 새로운 그 B 코디네이션이 되는 거예요. 그게 리니어 컨비네이션 코에피션트가 우리의 그 코디네이션이 되는 거니까, 그 코디네이션이 만약에 예를 들어 3, 7 이렇게 나왔다 그래요. 그러면 1제곱, 2제곱, 3제곱의 썸은, 합은 3제곱, 7제곱의 합과 같다. 그게 요 첫 번째가 의미하는 거예요. 그러니까 1, 2, 3가 1, 2,3 이게 요 UX에 해당하는 벡터고요. 다만 이 벡터를 이미 코디네이트를 누가 준 거예요. 그러니까 3,3의 이 벡터 더하기 7의 이 벡터라는 그걸로 이미 줬지만 UX는 그냥 그 전체를 생각해보면 이거는 1, 2,3이라고. 그죠? 네. 그래서 아까 이야기하는 게 UX는 이게 R100 디멘전의 여기에 살고 있다는 이야기가 이렇게 표현은 되지만, 왜냐하면 이 서브스페이스 안에 있기 때문에 이렇게 표현을 할 수 있지만, 그 점은 일단은 기본적으로 100디멘전짜리 쫙 숫자를 갖고 있는 애고, 걔네들의 길이 다 제곱해서 더한 그 길이는 그 B 코디네이트 그걸 그대로 갖고 와갖고 이 2디멘전al 벡터로 바꿨을 때 길이와 똑같다는 이야기가 돼요. 그것도 뭐 또 되게 이게 뭐 되게 어려운 것 같아 보여도 이거 생각해보면 되게 별거 아니에요. 옛날에 그 아이소몰피즘이라고 혹시 기억나요? 아이소몰피즘? 얼굴 이렇게 내가 쫙 뭐 어떤 남자 얼굴이 고양이 얼굴로 샥 바뀌고 그런 거, 영화에서 뭐 컴퓨터 그래픽스나 뭐 이런 데서 나온 아이소몰피즘. 그 아이소몰피즘 관련해서 얘기를 하면서 이게 100디멘전al 스페이스에 살고 있지만 기본적으로 B 코디네이션이라는 거는 이 전체 스페이스를 그냥 그대로 이 판때기 혹은 이 플레인을 이 3차원 혹은 이 플레인이 100차원에 살고 있을 수 있어요. 근데 이 판때기 혹은 이 플레인을 그냥 툭 띄워갖고 딱 세로에 붙여갖고 그 우리의 베이시스 축을, 새로운 X축, 또 다른 베이시스 축을 Y축이라고 하면 그냥 여기에 있는 2디멘전al 스페이스와 이 100디멘전al 스페이스에 살고 있는 이 평면은 그냥 정확하게 동일한 어떤 원투어 매핑이 존재한다. 이게 바로 아이소몰피즘이었죠. 그래서 이 평면이 예를 들면 100디멘전에 살고 있지만 이게 뭐 어떤 남자의 얼굴이었다면 이게 샥 바뀌어서 원투원 매핑으로 탁 이 2디멘전al 스페이스로 딱 오는 게 이게 뭐 또 고양이 얼굴이 되고 이렇게 되는 거라고 생각을 할 수가 있는데, 뭐 마찬가지예요. 이게 그러니까 여기서 이 벡터의 길이의 제곱은 이 벡터의 길이는 뭐냐면요. 이거 띄워버리고 x축, y축, z축으로 봤을 때 이거죠. 이거의 길이. 그 길이는 우리 Okay, so that was chapter 6.2. Then let's move to chapter 6.3. orthogonal projections. 네.
콜럼버스라는 게 그 길이가 1이라는
올소고널 컬럼?
네.
올소고널 컬럼은 올소고널까지는 그냥 각도만 수직이면 되고요. 올소 노멀이 붙었다 그러면 노멀이 붙으면 그러면 그게 길이까지 1이다라는 이야기가 돼요. Okay, so let's move to chapter 6.3. So it's basically the same thing, but it's a slight extension from what we learned in the previous chapter. So in the previous case, So we thought about the subspace where that subspace is spanned by only one vector. But now in this case we think about the subspace where we have like multiple number of basis vectors that are all orthogonal. So yeah, it's the same thing. So so let's jump into this theorem 8. Let's see. So suppose we have R4. Yeah, we think of any vector y in R4. And then also we think of the subspace W also living in which is also living in R4. And then this y, any vector y, can be decomposed into two parts, which is a y hat, and then this z part. And this guy is in our subspace W, and this guy is in subspace W perpendicular. Okay, and then in fact, this subspace is spanned by this orthogonal basis. So subspace W has p dimensional or p number of basis vectors, and they are all orthogonal. And then this y hat, which is a orthogonal projection onto that subspace, is represented in this form. Okay, so in this case, y hat is called orthogonal projection, and then since our basis vector is u1 through up, so they are so this y hat is in subspace W, and thus it should be represented as a linear combination coefficient of our basis vector u1 through up. And then their linear combination coefficient is obtained in this form. Okay, so that way we can obtain this y hat, which is orthogonal projection of y onto this subspace W, and then y minus y hat will be z, which is perpendicular to any vector in our subspace W. Okay, and thus it is included in, it is contained in this W perpendicular. So that is the theorem 8. So basically we briefly learned about this theorem, and what it basically says is any vector y can be decomposed into two parts, where one is completely belonging to a given subspace W, and also another part C, which is completely contained in W perpendicular. Okay, geometrically, if our subspace W is in this form, and then our vector y is projected onto y hat, and that is called this projection of y onto the subspace W. Okay, so let's see. Let's skip the proof. But it's quite obvious in this case. So we think of the basis for our subspace W, but our bases are orthogonal. So we think of two bases, which is, let's see, which is V1, and then this is V2, and they should be perpendicular to each other, and they are belonging to the subspace W. Okay, and then this orthogonal projection y hat is actually the summation of the orthogonal projection of y onto V1, and also orthogonal projection of y onto V2. Okay? So previously, what was the projection of some point onto a line? So in this specific case, where we have a point, and then we have a vector u, and then this guy is alpha u. So this was y, and this guy was y hat. So we learned about it. But now our subspace W is spanned by the two vectors, but actually the projection of this guy onto the subspace, which is y hat, is just a summation of the projection of this guy onto this line and this line. So so let's call this vector as u1 and u2, and so the projection of this y onto u1 is this guy, u1, u1, and then y, u1. Right? So we learned, or we derived this from this projection of this y onto this single line, right? But even if our subspace W is spanned by multiple orthogonal vectors, this y hat is just simply this guy. Okay? And then, yeah, it doesn't matter even if we have more vectors, I mean more than two vectors. Okay? And then let's consider the meaning of this. Okay? So we have to represent this y hat, which is orthogonal projection. But this orthogonal projection is decomposed into two vectors, the first vector and the second vector. And what is the meaning of this vector? So this vector is, so we consider this line, and then we project this y onto this line, so that the angle is perpendicular to this line u1. Okay, and then also we consider the projection of this y onto this line. Okay, so suppose this component or this vector as, let's call that as x1, the vector x1, and then this vector is x2. Okay, but this orthogonal projection y hat is actually the summation of these two vectors. Yeah, and then this is actually a rectangle, which means the length, I mean the angle between this and this should be 90 degrees, because u1 and u2 are 90 degrees, right? But what we know is also the 90 degree is in here and here, but actually 90 degrees are formed in here, and also here. So this is actually the rectangle, and thus this guy. So if we just take this part out, so this is origin here, and this is alpha 1 u1, which is the same as this guy, and then this part alpha 2 u2, which is the same as this guy, and then this vector y hat is actually the same as, or is represented as the summation of alpha 1 u1 and alpha 2 u2. So I'm not good at drawing these three-dimensional figure, but if you think about this figure a little bit more, and then you can easily understand the angle here are all 90 degrees. Okay. Okay, so that way we learned how to obtain the orthogonal projection of this guy onto the subspace W, and by the definition, this orthogonal projection, or this line. So here, let's see. So it's a little dirty. So So y is y hat plus this z. Okay, this z vector should be perpendicular to any vector in y hat, right? Yep. So we can easily derive this equation. So not y1. This z, which is y minus y hat. Okay, so y minus y hat should be orthogonal to u1, right? Because u1 is basically one basis vector for our subspace W, and also y minus y hat. Yeah, so these are all z's, okay? And z is orthogonal to u1 and u2, and all the vectors. Okay. So that is the useful relations when we kind of prove this theorem, and also when solving some other problems. So yeah, so let's see what we can do. So so in this example, so I gave the answer directly without too much of a proof. Okay, so these are the linear combination coefficient of u1 and u2, right? And then let's derive these guys. Okay, so suppose y hat is just a linear combination of u1 and u2. Okay, and then let's consider z, which is a difference between y and y hat, and that z, which is this guy, should be orthogonal to u1 and u2 as well. Okay, so this guy, z times u1, or the inner product between z and u1 should be orthogonal to each other, right? So y minus y hat u1, okay, so this guy, and then let's plug this guy in to here. Oops. And then if we consider y dot u1, and then we will obtain this guy, and then y hat dot u1. So y hat is this guy, and then consider the inner product with the u1. Okay, and then u1 dot u1 will be just obtained as this form. So it will be alpha 1 u1 dot u1, and then the second term is alpha 2 u2 dot u1, which becomes 0 because they are orthogonal to each other, right? So the answer for this will be just this guy. Okay, so so here the difference is, so I'm just considering this guy as alpha. Okay, so alpha 1. So in this case, so y dot u1, which came from here, and then minus alpha 1 times u1 dot u1. Okay, so let me rewrite it in this form: y dot u1 minus alpha 1 u1 dot u1 equals 0. Why should this guy be 0? It is because this c, which is this guy, should be perpendicular to any vector in W, and we picked up u1. Okay, so we just form the inner product of c and u1, and then since they have to be orthogonal, so the inner product should be 0. So that's why we obtained this 0 here. Okay, and then this alpha 1 can be obtained in this form: y in this form, right? So here in this proof of theorem, in this specific slide, they started from the answer and then verified this answer is correct. But in this case of my example, so we just represented this y hat as a linear combination, but we don't just know the linear combination coefficients yet, right? But we just derived alpha 1 in this form, okay? So that way we can prove this theorem or this representation by using this relationship of z being orthogonal to u1 and all the other vectors. And also from this equation, I mean, so you guys know how we derived from this equation, and then and reaching this answer for alpha 1. Okay, so the linear combination coefficient alpha 1 only involves u1 and our target, our vector, original vector y. So it does not involve u2 or u3 or any other u vectors, because they are all orthogonal. So here u2 dot u1 is always 0, so they are canceling out, right? So that way we can kind of we can intuitively understand this representation. So each of these linear combination coefficients is obtained by only considering that single vector. So when computing the coefficient of u1, and then we only consider u1. It doesn't matter what other vectors that we have, as long as they are all orthogonal. Okay. So that is one one beauty of this orthogonal vector. Okay. Any questions so far? 네. 네. 이 부분? 이 부분이요? 참 여기는 기본적으로 이 6장은 굉장히 쉬운데, 진짜 수직인 것만 알면 여러분 다 할 수 있는데, 이게 식으로 보니까 이게 막 되게 막 여러 가지가 나오는 것처럼 이제 보여서 좀 헷갈릴 수 있지만, 자, 일단은 수직인 것만 생각하면 돼요. 그래서 지금 우리가 뭘 했냐면, y가 있어요. 어떤 벡터 y. 그리고 y에 대한 정사형 수직으로 어떤 스페이스에 딱 착륙을 한 그 점이 있어요. 그게 y 햇이에요. 그럼 y는 이 스페이스 바깥쪽에 있었지만 이렇게 수직으로 착륙을 하면 얘는 이 스페이스 안쪽에 있어요. 그리고 이 점을 이제 이 스페이스 안쪽에 있기 때문에 이 스페이스의 베이시스 벡터들로 표현할 수가 있다는 거고, 그 베이시스 벡터로 표현을 하는 그 리니어 컨비네이션 코에피션트를 우리가 지금 배우고 있는 거고요. 그러면 그 리니어 컨비네이션 코에피션트를 어떻게 유도를 하느냐 하면, 포인트는 여기 y에서 이렇게 수직으로 내린 이 y hat, 그리고 그 차이 벡터를 생각해요. 이 z. 이 z는 이 평면에 수직으로 내렸기 때문에 이 평면에 아무 벡터를 골라도 다 수직이어야 돼요. 그러면 가장 쉽게 고를 수 있는 벡터는 그 스페이스의 베이시스 벡터들이잖아요. 그래서 걔네들을 하나씩 골라갖고 수직이다라는 식을 우리가 만들면 그냥 그 리니어 컨비네이션 코에피션트가 바로 나와버린다는 거고요. 그 바로 쉽게 구해진다는 거고, 지금 그걸 구한 게 이거예요. 그러니까 그 z 벡터, 이 벡터, 이 수직인 벡터와 첫 번째 베이시스 벡터 u1을 이렇게 갖고 왔어요. 그래서 걔에 대한 이너 프로덕트를 계산을 했어요. 그러면 이 z는 y 빼기 y 햇이고, 이 y 햇은 이게 내린 벡터, 얘는 리니어 컨비네이션 코에피션트로 표현이 될 거잖아요. 그래서 일단은 벡터 두 개, u1과 u2가 있다 그러면 알파1, u1, 알파2, u2를 이렇게 놨고 알파1과 알파2를 구하는 게 우리가 지금 해야 되는 일이에요. 그러면 알파2, 그러니까 u1이랑 이렇게 이너 프로덕트를 하면 u1이랑 이너 프로덕트를 하면 얘 빼기 y hat. 그럼 얘랑 얘 이너 프로덕트 한 거는 그냥 살아났고요, 여기. 그 다음에 두 번째 y hat과 이 u1의 이너 프로덕트는 y hat이 이거잖아요. 리니어 콤비네이션 코에피션트. 아니, 리니어 콤비네이션 of u1 and u2. 그 다음에 거기다 u1을 이너 프로덕트를 하면 다 날아가 버려요, 나머지는. u1만 살아남아요. 네. 그래서 이게 간단해져요. 왜냐면 다 수직이기 때문에. u1, u2 이런 애들이 서로 간에는 다 수직이기 때문에 자기 자신과 내적을 하는 게 아니면 다 없어져 버려요. 그렇기 때문에 이게 이쪽 내적이 없어져 버리고 결국 살아남는 거는 알파1과 u1 이너 프로덕트 with u1 이렇게 되는 거예요. 네. 그러면 다시 일로 와서 이제 요 텀만 남고 y dot u1 요게 여기서 나왔고 그 다음에 요거를 생각을 해보면 결국은 alpha1 times 요 이너 프로덕트 요 그대로 갖고 온 거예요. 네. 그게 결론적으로는 0이어야 되죠. 왜? 수직이어야 되니까. 그러니까 alpha1을 구해보니까 이렇게 나오는 거예요. 네. 지금 이거의 식은 요 리니어 컨비네이션 코에피션트는 알파 1을 u1만 갖고 계산할 수가 있어요. u1과 물론 우리가 시작한 그 y는 있어야 되죠. y. 네, 그렇게 알파 1이 결정이 되고 네, 알파 2도 역시 우리의 벡터 y와 u2만으로 결정이 됩니다. 답이 됐어요? Okay, then let's check one fact in this theorem. So in this theorem, this orthogonal projection y hat is always determined uniquely. So there is no two y hats. Okay, so it's really obvious. But if we project one vector onto any particular subspace W, and that orthogonal projection is always uniquely defined. So there is only one orthogonal projection. Okay. So if we just project it in an orthogonal way, and then there is no two different vectors that satisfies this condition. Okay. So that is also part of this theorem, and then let's briefly see how we can prove that. So given y vector, and then let's suppose we have the two vectors. So initially we were given y as y hat plus c, and also this guy is belonging to w, and this guy is w perpendicular. And then suppose there is another vector or another decomposition y hat and z1, y1 hat and z1. And this guy is also w, and this guy is w perpendicular. Okay. So the fact that z is belonging to w perpendicular means this y hat is orthogonal. This z vector is perpendicular to our subspace w, right? And so suppose we have these two different vector representations. So there is two y and y1 hat. Okay, so suppose they are different vector, so it can be having these two different representations. But they should all be y, so we can build this equation because they are all the same decomposition of y vector. Okay, and then we just manipulate this equation in this form, and thus by definition y hat should be in w, y1 hat should also be W. So this is a linear combination because they are just a difference, or linear combination of these two vectors where both are belonging to W, right? So it's a linear combination of these two vectors that are living in the same subspace W, and thus the linear combination of the two vectors in the same space W should also be W, right? So this is a linear combination of the two vectors that are contained in our subspace W. And in the same way, Z1 and minus Z should also be W perpendicular because each of them is living in W perpendicular and W perpendicular. And so the linear combination of them should also be in W perpendicular. And so the same vector, so let's call this vector, for example, as V, and this vector V should live in W and W perpendicular. Okay? So any vector from W and another vector from W perpendicular, they should be orthogonal to each other because that's the definition of W and W perpendicular. So we pick up any vector from one and then another vector from the other, and then their inner product should be 0. So the same vector V, which is this guy and this guy, so the inner product between these same vectors should be 0. Yeah, so that way it should be only 0 vector, which means y and y hat. Yeah, y hat. And this should be y hat. Okay, so these two vectors should also be the same, and z and z1 should also be the same. Okay, so that way there is no two different decomposition. Okay. Okay, so that's it for today. So let's continue next time. Okay.
어디서 끝내나? 어디서 끝내나? 딱 보고 해야 되는 거야. 장수가 나왔어. 내일 모레까지.